associate in Los Alamos National Laboratory. So he was there till 2015. He worked for about 2 years there, and he was director's postdoctoral fellow during this period. Up to he was fellow during 2015 to 2018, I believe. Later, he joined George Mason University in the year 2018, where he is currently serving as an assistant professor. Dr. Ghimire is also a resident collaborator at the Material Science Division of Kagome National Laboratory and a guest researcher at NIST Center for Neutron Research in Gothenburg, MD. As we all know, his research area includes topological and correlated materials, mesoscale magnetism, as well as crystal growth, and he has a greater in-depth interest and also contribution to the transfer properties. His research focuses in discovering and understanding emergent phenomena in quantum materials via designing and synthesizing materials and also measuring their magnetic and transfer properties. He has more than 100 publications, including about a dozen in a very good journal, having a very good impact factor, including Nature journals. His articles are cited by other authors more than 6,200 times within a period of 5.5 years. So according to Google Scholar, we all know his Yachts index is about 24 and I-10 index is 33. So we are very happy our alumni of Central Department of Physics is there and working a very important, contributing a very important work there. So thank you. I would like to express thanks to the speaker for accepting our invitation in a very short time. Thank you, Dr. Nirmal J. Ghimire. So I would like to invite you for the talk. मैले निमन्त्रण गरेँ, मैले राजु सरलाई पनि रिक्वेस्ट गरेँ हाम्रो च्याट बक्सलाई यसो च्याट बक्स अथवा अरू ह्यान्ड रेजहरुलाई केयर गर्नलाई रिक्वेस्ट गरेँ, हामी गर्छौं.
Thank you.
So
Thank
please,
you, sir.
Nirmal,
thank you
sir.
so much for this introduction. Let me see if you can see my desktop. Did I share my screen?
Yeah, yeah, it's nice.
All right, let me go into the. All right, can you see the? I cannot see myself. So can you see this presenters mode or the? It's coming the right thing.
It is right, coming right.
Okay, all right. Thank you, sir. All right. Thank you so much, Benil sir. So we are kind of following your footsteps. I was actually, it was a great privilege. I was your student working master's thesis with you. And, you know, we all get motivation from you and motivation from Mukunda sir was very incredible. And it has given us a long kind of very strong enthusiasm to remain in the field of, in the field of physics. And I'm happy that I'm still being able to kind of continue my research in this area. The field has slightly changed, but the enthusiasm has remained the same or has even become more stronger. So thank you for this. And I didn't realize that today was a special day to be, you know, presenting my talk in front of you in Guru Purnima Day is another happy moment. I think this is a very happy moment, and thank you for providing me this opportunity to present my research work in this platform. And it is very important, and my sincere thank you for this. Now, in today's talk, I'll basically talk about, give you kind of idea of what kind of research that we are doing here in George Mason University. And the title, as you can see, is New Quantum Magnets, Design and Discovery. And I'll kind of get into this, what that means in the next few slides. So first, let me start with what we do in my lab in George Mason University. So as I mentioned, that it's about crystal growth, material synthesis, and discovering certain phenomena in this material. So my primary tool is the growth of crystal. Let me take the pointer option and then in the laser. So this is these are the picture of some of the crystals that we grow in my lab. And to grow these materials, what we need in my lab is kind of furnaces, because we want to cook these elements, right? And then mostly what we work on is intermetallic system. So these metals get oxidized when they are heated in air, so they need to be sealed under vacuum or under inert gases. And we do that with, this is a sealing line where we create a vacuum and then seal these initial compounds, starting materials inside quartz tubes. Quartz is nice because it doesn't melt until 1200 degrees centigrade, slightly higher above 1200 degrees centigrade. And then we can do reaction inside those quartz tubes. And and then this here, you can see one of my undergraduate students was blowing one of those tubes here with the oxyhydrogen torch flame. Then, once we get these crystals, what we need is something to characterize them, what they are. Are these the materials that we wanted? What is their structure? So the structural characterization is done by X-ray powder diffractometer, and this is the X-ray powder diffractometer in my lab. It's a benchtop equipment. And then what we do is I'm sorry, I'm trying to get this minimized. Because it's on the way. Yes, thank you. And then this is a physical property measurement system, and it's kind of automated. So we can measure a lot of different things in this equipment. We can measure transport properties, for example, electrical resistivity. We can measure heat capacity. We can measure magnetic properties in this one, and it can go from 400 Kelvin down to 1.8 Kelvin. And it can apply magnetic field up to 9 Tesla. So we can do a lot of different measurements with these equipments that we need. Then this is my team currently. That includes 2 graduate students and 2 undergraduate students. There are a couple of undergraduate students who are not pictured here. And a postdoc will soon join my group starting August. Now, what is the research that we are interested in? And this is these are the materials that are at the intersection of electronic and magnetic topology. I believe I will kind of make it clear what these electronic and magnetic topology is. But the basic idea is that we wanted to study some materials that have very complicated arrangement of spins. So as shown in this sketch, there are these spins, and then its band structure had some sort of non-trivial topological properties. And I have a kind of a strong collaboration with people at George Mason University, especially with Professor Igor Mazin. He has a lot of experience with the DFT calculus, and he's an old expert. He spent about 30 years in Naval Research Lab and joined our department last year. And you can see later in this talk, that we have started a very strong collaboration with Professor Mazin. We also collaborate with Professor Vora, who is an experimentalist doing some optical measurements. Professor Gari, also another experimentalist who does STM and quantum Hall measurements. And Predrag Nikolic is a field theorist. What are we doing, experimentalist with field theorists, is that a lot of different things, different kind of these magnetic textures and electronic properties that have been discovered now in the materials were once discussed in quantum field theory and never realized in high energy physics, but now these things have been realized in real materials. So that is a connection point to work with field theory. And I also collaborate with people around the United States and also overseas. So basically, NIST this is National Institute for Standards and Technology, which is nearby. It's about in 40 minutes drive from George Mason University. And I have a kind of strong collaboration with more than 3 groups now at NIST. And I still collaborate with people at Oak Ridge, where I spent time doing my graduate research, and at Argonne National Lab, where I did my postdoctoral research. Then still at Los Alamos. Los Alamos has this high magnetic field lab that in which the magnetic field can be applied up to 60 Tesla. So if we need in a material to probe with high magnetic field, we collaborate with people there. And we have recent collaboration with Professor Alberto Morpurgo at University of Geneva in Switzerland. So, the outline of this talk is I'll start with giving you a kind of background of why this topic is interesting and things like that. Then I'll kind of, briefly give you a background of what is conventional and what is quantum magnets. Then I'll kind of show you some of my results that we recently obtained in 2 compounds, that how we designed this and what we discovered, right? So this is one of them is cobalt-93 sulfur 6. Another one is this yttrium magnesium 10-6, and then I'll conclude with the summary. I express my sincere thanks to my collaborators, without whom the research would not have been possible. So it includes Professor Igor Mazin at Meson University, my students, and Dr. Jeff Lin, who is a NIST fellow. NIST fellow is the highest level of scientist that one can get a position in NIST. So this is, and Leif was a postdoc with Jeff. And now he has moved to industry, and Rebecca has joined Jeff. So we are collaborating with Jeff and his group. Then I still have collaboration with people at Argonne National Lab, as well as at Oak Ridge National Lab, and some of the measurements were done in all these places. Now, why magnets, right? The question is. Magnet has a very rich history, going back to 6th century BC, when this lodestone was realized. People discovered this lodestone, and they used in navigating compasses, not certainly in this form, but in certain forms. But then magnet is ubiquitous now. It is everywhere in our cell phones, in the vehicles that we use, and it is used in clean technology. It is used in medical devices. And it is used in computers and data storage. Actually, it changed the landscape of data storage with the use of this magnetic read heads in these hard drives, right? That happened in 1980s when spin bulb, Stuart Parkin discovered this spin bulb. Now magnets are everywhere, and people are using since ages. Now the question is why we want to do more study on magnets. That's an interesting question, and to answer that, I'll kind of like to take you to this picture, which I like a lot, and I kind of put in almost all of my talks. This one, and this was kind of published in one of the reports submitted to the Department of Energy. And what it says is that, if we look into the evolution of human civilization, our history has been marked by different materials, actually, right? We talk about Stone Age, we talk about Bronze Age, Iron Age, Silicon Age, and it has, in each of these materials have the hallmark of changing our civilization. When bronze was discovered, it was a big deal at that time, because now people found another interesting tool instead of stone, and human civilization marked a jump there. And I don't have to exaggerate the thing how important iron was at that time, and it is still important. And the importance of the silicon, right? We can still imagine, when I was working with Binisal, we used to use floppy disks. Now, no more. People probably won't see floppy disks anymore, probably in the museum, right? So, and that has happened with these silicon technologies in the recent years. And if we want to now make our civilization, take our civilization to the next level, what we need is it should come through a material, right? That is why we are interested in finding new materials, and especially why quantum materials. There are different types of materials people are interested. Why especially these quantum magnets is that there is a big kind of this surge in using spin as another degree of freedom for the technology, right? Electronic technology, which is called spintronics. And it has, as I mentioned, it has already started its use in the read heads of this disk that was discovered in 80s. But there are still more things that can be done. So what we can think of is like if we have racetrack memories, can develop racetrack memories based on these different magnetic textures, then our storage capacity will be very efficient, and it uses very less power. So maybe we can think about storing all the information that we can collect in a cell phone, and without having to charge for several days or months and things like that. So less consumption of energy in the electronics, faster electrons, thinner electronics. If we have to go into those, then what we need is these new materials with new properties. So that is kind of an interest or drive to look for the new quantum magnets. Now, I'll take you to the introduction of these magnets. And before going into quantum magnets, let me start with what the conventional magnets are. We know that from our school level of study that in a paramagnet, the spins are all kind of randomly oriented, right? This is a disordered system. And in a ferromagnet, the spins point all in the same direction. There is a net magnetic moment that is measurable. That is what attracts other magnets. And in the antiferromagnet, it is still an ordered state. But what happens here is that the moments cancel each other. So there is no net moment. So a magnet doesn't attract an antiferromagnet, but still it is a magnetic state, magnetically ordered state. And there is a ferromagnet where spins are pointing just like in antiferromagnet, but they do not cancel perfectly. So it has still a net moment. So it is kind of a hybrid between a ferromagnet and an antiferromagnet. Now, what are topological or quantum magnets, right? So this definition is very vague, but how I like to define these topological magnets or quantum magnets is that a magnetic system that have a very interesting quantum mechanical phenomena that gives them a measurable property that they display, right? And that kind of magnets include these non-coplanar ferromagnets, and I'll get into that a little bit. These still behave as a ferromagnet, but these are kind of a non-coplanar. They are not in the same plane like here, right? All the spins are in the same plane. They are not in the same plane. Non-collinear antiferromagnets, where we have these spins pointing in very different directions. This is an antiferromagnet. Still, the spins cancel each other, but they are not collinear, right? Here, these antiferromagnet, these are collinear. They lie on the same line. Here, they are in different axes, pointing in different axes, but still an antiferromagnet. Or a very complex kind of magnetic texture, which this is called a skyrmion. This name was again borrowed from the high energy physics. And what happens in this kind of spin texture is you have all the spins pointing up here. You go to the next level, the spins kind of tilt a little bit and remains the same in this layer. And as you go down and down, it kind of continuously rotates, and at the center, it is pointing all in the opposite direction. So I'll get back to this, why these are interesting, why we can call them quantum magnets or topological magnets. I'll take you to kind of a very basic level of quantum mechanics here. Just a promise. Also, these equations only on this slide. This is a Griffiths level quantum mechanics this is in the second part. So what Griffiths kind of discusses here with this example is non-holonomic processes, right? So this is kind of earth. Why he gives this earth is that because earth has this bulging and there comes this curvature. We can take a globe and do this experiment ourselves. Instead, we don't need to take pendulum. We can make a vector. And when I was teaching the course, I actually have done this with my students. So take a pendulum here and move this pendulum through the earth to the equator, move all the way down here and come back in such a way that it has to be adiabatic, means you don't want to juggle this, let it swing smoothly. And in this case, if it is swinging in this direction, what will happen is that it will start swinging in a different direction. And what that means is that this pendulum will make an angle between the initial position and the final position. And that angle depends on the path of that which it rotated. And it comes purely from the geometry of the curvature, right? And nothing else. And this angle this angle depends. I mean, the rotation depends on the solid angle subtended by this path at the center of the Earth. And this is equivalent to what we call now a Berry's phase in materials that the electron can acquire when electron move through certain these curvatures in materials. For example, the kind of magnetic structure I showed you in the previous slide, when we have that type of magnetic texture, electron can pick up this geometrical phase moving there. Or if there is interesting band structure in the material, the electron can pick up, moving in those curved spaces, can pick up the Berry's phase. And this Berry's phase has this kind of formula, especially the line integral. This is this is a certain state of wave function, and then this is a final state is also the same. And there is a kind of phase factor. That phase factor, this only is a phase, right? And so what is the consequence of this? Why this Berry's phase is interesting is because, let's look into this, flux. Flux this is definition of flux, right? This B dot dA. Then, we can take B as del cross A, and then take and change it to a line integral with using Stokes theorem, and we get into this form. So this equation and this equation has a similar form, except that in this case, B has to take this value, right? In that case, this Berry's phase is equivalent to the flux of a magnetic field. So this is a very important concept, and this has changed, the Nobel Prize that people got in like a couple of years ago in topological materials has the heart in this Berry's phase. Okay, so why this is interesting is that this is now equivalent to a magnetic field. So an electron moving in a material can pick up this phase, which it feels like a magnetic phase, but there is no real magnetic phase. So this is a fictitious magnetic field that an electron can experience in a real material. So how do we know that an electron can actually experience this phase? While moving through these different type of spin textures. It happens in all these magnetic texture, and it has been measured. So what is the reason to be able to measure it is very simple. So now there is a magnetic field, and there is a charged particle moving through this magnetic field, right? So what happens in this case is that you experience a Lorentz force, and that Lorentz force comes as a Hall effect, and we know all about the Hall effect. It develops a potential here, and that potential you can measure. Actually, it is the Hall effect is a property of all conductor. So if it is a normal conductor, then it should look like this. The resistivity should look like this. That means this is a magnetic field. The resistivity should be linear to the magnetic field, right? So it should look like if we plot magnetic field, and this B is mu naught H. So this should be a kind of a linear straight line. But when there is a ferromagnetism in a material, this M is a magnetic moment because of a ferromagnetic ordering. Then it was Hall, he discovered this like more than a century ago, both Hall effect and anomalous Hall effect, that this Hall effect will experience a component that is proportional to the magnetization. So let me show you how the magnetization of antiferromagnet and ferromagnet look like. This one is, this is magnetic field, and here is magnetic moment. So in antiferromagnet, the magnetization curve is a straight line. In a ferromagnet, this is a soft ferromagnet because you can, when you turn the field off, the magnetic moment becomes 0. And then it kind of goes and saturates here. This is a hard ferromagnet because it has this hysteresis, right? So if I measure Hall effect on these different materials, what I should see is something like that, because it should be proportional to magnetization. Just like here, it should give this behavior. Just like here, it should give this behavior. And here, in case of antiferromagnet, it should give this behavior. But if there is a Berry's phase, and that I discussed in my last slide, it should give another extra component. And if we see that extra component, then we can know that this electron is experiencing that extra component. And that field is huge as compared to the field that we can apply. Actually, people have done calculation on these type of spin textures, how large that magnetic field can be. And it can be as large as 4,000 Tesla. And in a lab, in a national lab, the maximum field that people have generated is about 100 Tesla. So this huge internal magnetic field that kind of forces the electrons should give rise to very interesting properties, right? And that is what that is why this Berry's phase is interesting. And in fact, as I said, in ferromagnet, getting this anomalous Hall effect is not a new thing. It has been known for more than 150 years now. But in antiferromagnet, as I discussed here, it should be a straight line, right? And that was kind of understood, taken as understood for many years. And it was in 2012, 2013 timeframe. There was a theory paper, and they say that, oh, if you have this type of antiferromagnet, it is an antiferromagnet. But still, because of this geometry of these spins arranged in this triangular triangles, you can get this Berry's phase, and that Berry's phase can give rise to a large anomalous Hall effect comparable to the ferromagnets. And actually, in 2015, this group in Japan actually measured this anomalous Hall effect. This is a Hall effect, and you can see this large value, very comparable to, looks like that of a ferromagnet. But if we look at the magnetization, there is a small jump. Without having a small magnetic moment, we cannot detect the anomalous Hall effect. That's kind of an irony. We need a small moment. But this is like milli Bohr magnetron, which is 1,000 times smaller than in an iron. But this value is comparable to that of iron, or even larger. So where is it coming from? So that was one of the confirmation in a non-collinear antiferromagnet that the Berry's phase is there, and it was measured. So just in this Nature paper, this was the main theme of that paper. And then now here I will show my own result that if now in non-collinear antiferromagnet, people kind of now proposed in theory that you can see the anomalous Hall effect and people observed. But in a collinear antiferromagnet, there is no way that you can get a Berry's phase, right? But I'll show you my result that I found this large anomalous Hall effect in one antiferromagnet, and it has developed new theories now. So this is the collinear antiferromagnet of this particular material that was reported along the magnetic structure was reported a long time ago when I put the atoms, these spins in different atoms look like this. And it was, again, the Stuart Parkin who discovered this spin Hall, this spin valve was the one who was doing this experiment in 83. So it's a collinear antiferromagnet so far. Since I grow crystal, I like to show the picture of the crystal. Though there is nothing much I'll talk about this. There is a nice crystal inside the tube before I open the tube, and these are the crystals grown in my lab. And then, it has this magnetic moment wise. This is a collinear antiferromagnet, but it has a small magnetic moment, just like in that magnet's 310 I showed you before. This is again 0.001, 1,000 times smaller than you have in a ferromagnet, but it gives this anomalous Hall effect, large anomalous Hall effect in this material. And it come as a surprise to me when I first measure. It was hard for me to explain this because there was no theory that could say that, okay, in a collinear antiferromagnet, you can have a large anomalous Hall effect. So initially what I thought is that, this anomalous Hall effect could be because the magnetic structure could be wrong in this material, or, it could have this, again, non-collinear or non-coplanar spin structure, but we did some Newton experiments and we didn't find that in any of those signs of those things. Then, when we looked into the band structure, not knowing that, okay, what kind of spin texture it has been forming, we did this calculation in paramagnetic state, actually. And in the paramagnetic state, this has this linear crossing of bands very close to the Fermi energy. And if you have magnetism and if you have this type of band structure, this is called the Weil node. And this can give rise to anomalous Hall effect, and it is known. So when I wrote this paper, I kind of just saw the possibility that, oh, this can happen. But people followed this, and now this result is published in Science Advances, that they did calculation exactly on this system with the collinear spins. And they come with a very interesting theory now. What they say is that this material has a crystallostructure that lacks certain symmetry elements. And due to the lack of those symmetry elements, it allows the time reverse symmetry breaking, although it is a collinear antiferromagnet. Therefore, in such materials, one can expect, or they calculated this Hall conductivity, that it has non-zero Hall conductivity, and you can measure it. And it was interesting that the value that they calculated and the value I reported in this paper were very similar. And one of the things that proposed is that, okay, there is a Berry curvature here in one of these bands in this material, and that can give rise to the anomalous Hall effect. So that's pretty nice, because now we know that okay, it's not only non-collinear, we can have this kind of topological Hall effect or anomalous Hall effect in collinear antiferromagnet. Also, in nature, you have more collinear antiferromagnets than non-collinear, and usually these exist in high temperatures also. This has kind of opened a new avenues for the research, and a lot of people are interested in this kind of materials now. And it is because now there is another theory also that kind of supports a similar kind of result, which I'll get back in a second. And we followed this experiment, and I sent this sample to Geneva in Professor Albert Murpurgo's group. And what he did is he kind of thinned down the samples to nanometer size, and then he again repeated the measurement. When he thinned down the sample, what happens is that the conductivity kind of increases by a factor of 10. So maybe it is the cleanliness of the sample, or some sort of surface that develops. We don't know that yet, but certainly the conductivity increases by a factor of 10 in thin samples. Say this is the value that I measured in bulk, and this is the value they were able to measure in the same crystals that I made, right? Similar crystals that I made. And another interesting thing that they found is that the Hall conductivity increases significantly and reaches about 60% of the quantized value. If it becomes like 1, this would be a quantized Hall effect. And getting a quantized Hall effect in an antiferromagnet is not something that we can assume in a collinear antiferromagnet, right? But it had shown some signs that if we can play around with this material, maybe we can reach there. So this is one of the things that I am currently working. And there is another hope for this, is that in this paper, what they showed is that actually in this type of collinear antiferromagnet, the Hall conductivity, this is a Hall conductivity plotted on y-axis, and there is a chemical potential along the x-axis, the mu is chemical potential, which is the Fermi level. So this Hall conductivity is very sensitive to the location of the chemical potential. If you change the chemical potential slightly, maybe from here to here, then you can see a drastic change in the Hall conductivities. And this result is very new. It was published in 2020. I know these. I know very well the people who are doing the theoretical work of this thing. But I was doing on my own. Before knowing this result, that I had started doping this cobalt 9-3 sulfur 6 to see if we can tune these properties, right? So this is a 10%. This cobalt 9-3 sulfur 6 pure parent compound, and this is the 10% iron doped. So iron puts holes in it. So what it does is that it kind of lowers the Fermi energy. And then in this case, what we got is that, see, the sign of this Hall effect completely flips. So maybe we are pushing it somewhere, and we don't know where we have pushed it. Some in certain ways that the Hall effect has reversed its sign. What it suggests is that this Hall effect is tunable, and it opens the possibility maybe to look if we can achieve this quantization of the Hall effect in this material. And this is one of the things that we are working in my lab right now. So with this, I would kind of wrap up on this material, and I will kind of show you the another interesting result. Recently, I recently submitted this paper earlier this week, and this is a new, again, an exciting result. According to me, we have kind of found a new mechanism for the topological Hall effect in this material, and we give a new name to it, and it's called nematic chirality. And people have not discussed this before. And this is in a compound yttrium manganese 10-6. So this is a Kagome net or a Kagome lattice magnet. And what is a Kagome lattice is this name comes from this Japanese basket. And we see this quite often in Nepal as well, right? Our own TU's logo is something similar to this. And here you have all these triangles, right? Connected by these hexagons. So this is Kagome net, and if we look at into this is a structure of this material, yttrium manganese 10-6. These green balls are yttrium. These black balls are all manganese. They are all equivalent. Here. They are all equivalent, and all other colored red, blue, and the gray are tin. So in this layer, if we look at into this layer where these green balls, they are arranged exactly like in this pattern here. So that's why this is a Kagome lattice magnet. And then this material is interesting, has very interesting structure in a sense that all these manganese are equivalent structurally, but they are separated by inequivalent blocks. Here, between this and this, my apology. Between this and this, these manganese layers are separated by just tin atoms. And here, these manganese atoms are separated by tin as well as the yttrium atoms, right? So what it does is that it changes the interaction between the manganese in this layer and this layer, and the interaction between manganese between this layer and this layer is different. Right, so that's why this is represented by these Xn constants J1 and J2. They are different, and it can lead to a paramagnetic frustration in the system, and it can give rise to very interesting properties. And these Kagome lattice magnets are well known for having a very interesting electronic structures, also topological electronic structure, flat bands. And there was a recent paper in which our own Professor Madhav Ghimire was a co-author, and we happen to write a news and views article on this material, where we have kind of written about the importance of these topological Kagome lattice magnets in electronic properties. So if you are interested, you can access this paper. And then, because of this kind of paramagnetic frustration, it gives rise to very interesting magnetic properties. Especially, the magnetism here is very complex. Complex in a sense that it is not a antiferromagnet. It is not a ferromagnet. It behaves like a ferromagnet. It behaves like an antiferromagnet, but it is in a sense that it is a helical magnet, right? And it is not also a helical magnet. There are two helices. These layers correspond to different layers of these manganese atoms, and these arrows represents spin. All the spins are pointing in the same direction in one layer, and when it goes to another layer, it rotates slightly, and it rotates very non-trivially. It rotates kind of minus 20 degrees here and then about 110 degree here. So there is a difference between 90 degree of difference between this and this layer. So what it does is that it produces two helices. This red kind of spins make one helix, and this makes another helix. And this was reported, long time ago with the neutron results done on powder samples. So powder samples aren't always that reliable, but we kind of confirmed this, and it has this type of structure. And this complexity in magnetism, with the complexity that it was showing in magnetization measurement that was reported in the literature, and I could measure this. This is my measurement, but it was this kind of plot was already reported. What happens is that the properties along c-axis is pretty boring. It's continuous here, also continuous, the red ones. The blue ones are interesting. So there's a jump here, and this jump is not uncommon. We see in a lot of material. What does here is pretty interesting, and this is kind of unexpected and not seen in many materials. So I was interested mostly because of that, and then the fact that this material can have electronic properties. And I'm telling you how we think about what material to make, and then what material what material could be interesting in terms of the physics that we are interested in. The design strategy, right? So this is the crystal, one of the crystals, and we did actually, in fact, we did a lot of neutron measurement on this particular crystal, and these students were involved in this research, and we were able to map out the phase diagram, and it's showing like here this is one phase, and this is another phase here, which is this region. This is another phase, which is this region. What I'm doing is I'm putting these kind of plots at many temperatures, right? And then producing the phase diagram. And there are little phases here and there, and then goes to a ferromagnetic state. I'll not go into the details. And one thing I found when I started measuring this was that this is the Hall effect. The red curve is the Hall effect, and the blue curve is the magnetization. So as I mentioned you before, if it has a ferromagnetic behavior, that ferromagnetic behavior has to be linear with the magnetization, right? But this Hall effect is non-linear with this magnetization. So it was kind of indicating that it could have some sort of additional Hall effect in this material. In fact, it does. And while I had just finished the measurement, and there come a paper in archive from China, obviously, and then they reported the same thing in this paper. And they kind of mapped out the phase diagram, and this is where this is mostly concentrated at higher temperature, and this is very important for the thing that I'll be talking later. It's only at higher temperature. It is mostly centered at about 245, 250 Kelvin. Okay. Then what we did is we wanted to understand now what is causing this. Is it the spin textures, just like I showed before, it's non-trivial spin textures, or is there a new phenomena that is going on here? That is what we wanted to understand in this material. So we carried out neutron diffraction in single crystals, which was not done before. So Lake actually started it when he was still a postdoc with Jeff, and this is basically actually measured by Lake. And later, Rebecca took it over. And then basically, I'm not going to talk details about it, but I can tell you that this structure we verify here. And then, this whole thing, these two peaks correspond to a helical state. And since we have two closely spaced peaks, those corresponds to these two helices, intertwined helices, right? It's like intertwined helices. We call it staggered helix. Then, or staggered spiral. Then our motivation was to do the neutron in field and see if we can understand anything about these behavior we are seeing in magnetization measurement. So these two peaks are the same peaks. They are looked through a different angle. So the same peaks, and this is a nuclear peak. Nuclear peak doesn't change, but the magnetic peaks are one that are expected to change with the change in magnetic structure, right? So, up to about 2 Tesla, there is no much change in this peak. Even intensity doesn't change. This corresponds to this region. And then at the metamagnetic transition, what happens here, it kind of changes the intensity, which is kind of expected, but it also changes a little bit of this, it goes towards right a little bit. right? The Q vector changes. Now, when I reach here, then what happens is that it again comes back. It doesn't come back to this same position when we zoom in. It goes to a different state. When it goes to a different state, it gives another additional peak here, right? And this corresponds to this region. And what we did is we mapped this out through the temperature. So we found that even in 100 Kelvin, the same feature exists. And we were able to kind of match this behavior that we were observing from neutrons. What neutron does is that actually it can see the ordering of the spins. So that is what we are kind of probing here. We confirm this phase, we confirm this phase. This phase is where this thing happens. And then this phase is where we see this double peak feature. And then this is a ferromagnetic state when we don't see anything besides the nuclear peak, because all the intensity goes to the nuclear peak in the ferromagnetic case. We were even able to see these tiny little things at 300 Kelvin. You see at 2 Tesla, a new peak appears, and every details we were able to track with the Newton experiment on this one. And then of course that alone does not give us like the microscopic understanding of what is happening in this material. Right now we needed a theoretical support to understand modeling, right, what is happening here. So for this, now we were lucky to have Professor Mazin in the department. When I saw this data to him, he was interested, and it didn't take him a long time to do this calculation. It took me a lot of time to understand myself, but I'll not go through this. But I'll kind of explain what that result is. Okay. So what he did here is that this is the kind of the magnetic structure here. Now, first, he did a calculation for a magnetic field applied along the z-axis, and this is energy versus the magnetic field for this state. And what happens is that this is the red curve is what his result is, and you get a red curve. Then he applied magnetic field in the plane where all these interesting things happens. When he applied magnetic field in the plane, then what happened is that he get this blue curve. And because this has this single ion anisotropy or single site anisotropy, what happens is that there is an energy cost, right? So it is obvious to think that this spins will have hard time remaining in the plane and retaining that spiral state together. So to minimize the energy, these spins have to flop into a perpendicular plane. And based on that, he did a calculation, right? This was kind of, just to show you little to be more clear, this is not exactly what the spin structure is, but this is what this structure look like, right? The spins are in the plane, and then they are kind of constantly rotating along the z-axis. The helix is along the z-axis. So in another case, what happens is that when magnetic field is applied in this direction, and the kind of this spiral, now all the spin flop to the perpendicular plane, but it still has to maintain that spiral state. We know that from the experiment, right? So this becomes a cycloidal state, not a helical state. This is somersaulting type of helix. It's called cycloidal state. But because of the magnetic field, these moments has to cant along the x direction, right? So this is what this green curve is. And if we look at into these three curves together, so this is in this region, I'm magnifying this region here. What happens is that at low field, this blue curve, so that means the planar phase has minimum energy. But when you at this phase H1, which that metamagnetic transit happens, what happens is that this flopped phase has the minimum energy. So the magnetic structure has to change at this stage and go to the spin has to move to a perpendicular plane and still giving rise to this spiral state. And during this process, what happens is that the wave vector changes a little bit. And that is where we see the change in peak. We understand that. And in this region, what happens is if I zoom here, I can see again that at this field H2, these blue dots are lower than the green one. So the energy in this region for this planar structure becomes minimum than this structure. So this helix again flops back into the plane. and forms another different type of magnetic structure, which gives rise to this two-peak feature. And we know exactly why the two-peak feature comes. So we were able to understand with this theory, we were able to understand all the different magnetic structure. And this is not very usual. Each individual phases may be usual, but appearing in the same material is very unusual. Right now, we understand, combining all these things, we understand everything that I was measuring in this crystal. So here, there is this planar phase. Here, it goes to what I call is called transverse conical phase. The moments are not in the plane, but out of plane, but they are still tilted towards the direction of the magnetic field. So they make a cone. So we call it transverse conical state. And when it goes to this region, the spin again flop back to the plane, but their rotation is very different from this distorted state. So we gave this a new name called fan-like structure. And in the fan-like structure, what happens, the projection of these atoms on x-axis and y-axis is different, actually twice. So we see this peak and that peak exactly at twice q. This is at 0.25. This appears at 0.5, and only in this region where this thing happens. So everything is coming very beautifully. And then he calculated the magnetic moment again, as a function of the magnetic field, and he could reproduce exactly what we see in the magnetization, right? Quantitatively, not the qualitatively the field may be a little bit different, which is kind of expected, but qualitatively it's kind of exact same. So now we know all the magnetic structures in this material, right? This is in itself very interesting. We were able to solve this problem. Now the question is, what is giving rise to this anomalous Hall effect or the topological Hall effect is the question. We didn't see any kind of structure that possibly could give rise to this this topological Hall effect. That made us think, and why does it happen only at high temperature? That is another thing, right? So this is how, I'll not go into the detail, but this is how we estimate this topological Hall effect. The black curve is the measured one. This is calculated for anomalous Hall effect based on the magnetism. And then there is a kind of a normal Hall part that we can subtract. In this one, it is a little non-trivial, so I kind of tried different models. And this is the difference, and this is the topological Hall effect, and it is finite. And this curve is what I plotted here. I'll tell you what this theory is in the next slide. So there is definitely a finite topological Hall effect in this material at certain temperature ranges, which kind of is pretty large at about 245 Kelvin. Now we know that none of these mechanisms that I explained you earlier is true here. So what should be giving this topological Hall effect is what now we have come up with the explanation for this also. And this has very this has a lot of similarity with the pneumaticity of iron-based superconductors. And what happens here is that it comes from this spiral state. Even just to take a single spiral, that single spiral is not able to give a topological Hall effect. But then at high temperature, what happens is that there is fluctuations. So when you add fluctuations to this system, then what happens is that the population of the right-handed helices and the left-handed helices, they kind of change because of the fluctuation. And we have all these calculations for that. And when it imbalances, then when we calculate the field, topological field for that state, then it becomes non-zero. And this topological field gets this formula, a very simple formula in terms of the magnetic moment, which I can measure. This is saturated magnetic moment again. It's the same thing. And this is temperature and magnetic field applied along the x-axis. So these are all kind of measurable quantities in the lab. So, and this is a constant. So I can put a proportionality constant and make it resistivity, the field, because this field is proportional to resistivity. As we know that the Hall effect is caused by the magnetic field, right? It is that internal magnetic field. Now, when I used my data and then plotted this formula, I get this blue curve, and it is the matching between this experiment and theory is amazing. And then another thing is, if we look at into this formula, where mz is used, and this g component of the magnetic moment remains surprisingly constant as a function of temperature. So taking this as a constant, what happens is that this resistivity should vary linearly with the temperature, right? For a constant magnetic field. And here in the inset, I show that this is for 4 Tesla, that actually this topological Hall effect has a linear variation with the temperature. So every aspect of this theory matches with the experiment. And now here we have a new mechanism that we name a nematic spin chirality for the origin of the topological Hall effect. We are kind of a little excited about it, and the paper is submitted earlier this week, and let's hope how it goes. The editor likes it. So now I'll summarize the talk. So basically my research is synthesis-based materials research, and we are interested in materials at the intersection of magnetic and electronic topology. I did not go into the electronic topology in this talk, but I certainly showed you interesting phenomena that we recently kind of discovered in 2 systems, right? One was very unexpected collinear antiferromagnet. That theory at the time when I found that, there was no theory for that. Now several theories have come, and then I kind of went through this new mechanism of this nematic chirality for the topological Hall effect in this compound yttrium-manganese 10-6. And it may again open a new avenue of research for looking for these kind of topological textures, not only in these complicated structures, but due to the mechanism of the thermal fluctuations in other materials also. We have a couple of materials already in mind where this could be the reason for the Hall effect, and those are yet to be measured. With this, I'd like to thank you for listening to the talk, and I will take questions that you have. Thank you. Hello.
Thank you very much for this magnificent in-depth talk. I request Raju sir.
Ajay, Binil sir.
If you have gone through the chat box questions.
Yes, of course.
It's the time for
Binil
questions.
sir,
Please,
thank
sir.
you a lot. Thank you so much, Binil sir. विशेष गरी निर्मल जी घिमिरेलाई यो यस्तो कुरामा इन्ट्रेस्टिङ टक दिनुभयो र आई एम श्योर त्यसमा थुप्रै क्वेसन छ र च्याट बक्समा थुप्रै क्वेसन आइसकेको छ, ह्यान्ड रेज पनि भएको छ, तर पहिली च्याट बक्समा टाइम अनुसार म यो क्वेसनहरुलाई लिन्छु। यसमा सबभन्दा पहिले हाम्रो रुद्र काफ्लेजी प्लिज म एकैछिनै म यहाँ अनम्युट गर्ने पनि कोसिस गर्दै गर्छु। यहाँ म सबैलाई अनम्युट गरिदिन्छु, तर प्लिज आफूलाई नचाहिने भएको बेलामा माइक अन गर्नु होला है, तर फेरि सबैलाई म्युट गर्नुपर्छ। रुद्रजी प्लिज गो अहेड।
ओके निर्मल सर, एकदमै एक्साइटिङ, भेरी नाइस टक, थ्याङ्क यू सो मच है। मेरो एउटा क्विक क्वेसन चाहिँ यो जुन बेरी फेज छ नि,
हजुर सर,
बेरी फेजले चाहिँ दिस गिव्स राइज टु Aharonov-Bohm effect, is that right?
Yes, that's correct. It's equivalent to those things are connected.
भनेपछि अर्को एउटा कुरा चाहिँ सरले त्यो जुन म्याग्नेटिक फिल्ड मेजरमेन्ट भन्नु नि अबाउट 4000 टेस्ला, that is really high magnetic field, हैन? त्यो त धेरै नै हैन?
It is, and this can be calculated very easily with all the parameters that I have, and it's a very high field. That is why I think it can change the dynamics of the electron inside the material and can give rise to new properties, and that is also at the core of all these topological materials.
Thank you so much. Thank you.
You're welcome.
त्यसै गरी नेक्स्ट म प्रभाकर ओलीजीलाई रिक्वेस्ट गर्छु। प्रभाकर जी
सुनिरहेछ सर?
यस, प्रश्न छ, भन्नुस्।
यसमा त्यो रेजिस्टिभिटीहरु त्यो निकाल्दा जुन यो टेस्ट गरियो त्यसमा चाहिँ त्यो स्पेसिमेनको थिकनेस, बल्क, त्यो थिकनेस चाहिँ कति माथि गरिया थियो होला?
That's very interesting question. त्यो thickness चाहिँ त्यो usually कस्तो हुन्छ भने resistivity measurement मा the smaller the thickness, the better result you get. We usually measure in sample with 200-300 micrometer. I mean 0.2, 0.3 millimeter. But smaller you can make, the better result you get. त्यो मैले अहिले देखाउँदाखेरि त्यो एकदम हाम्रो स्याम्पललाई थिन बनाएर न्यानोमिटरमा पनि लगेर मेजर गरे एउटा त्यो कोबाल्ट म्याग्नेटिक सल्फेट त्यसमा चाहिँ रिजल्ट चाहिँ
in your case
about several nanometer. In my case it was about 5 to 20 micrometer.
Okay, thank
you. We in my lab what we do is we mechanically polish those with using sandpaper to make that thin. And some materials are brittle and they break. We can make it very thin. Some materials are good, and then we can go down to pretty small thickness.
Okay, thank you Prabhakar for the question. Next, ma ekaichhina Madhav sir lai ekaichhina request garera Shambhu Ghimire ji, please go ahead. Shambhu ji.
Thank you Nirmal ji, very nice talk है. मेरो चाहिँ तपाईलाई थाहा छँदैछ म चाहिँ लेजरमा काम गर्ने मान्छे है. अनि यो तपाईहरुको यो यस्तो इन्ट्रेस्टिङ यो म्याग्नेटिक टोपोलोजिकल प्रोपर्टी जुन छ यो स्कर्मियन लाइक प्रोपर्टिज यो चाहिँ लाइटको हेलिसिटीसँग कपल गर्छ कि गर्दैन होला, जस्तो लेफ्ट ह्यान्डेड र राइट ह्यान्डेड लाइट पठायो भने यसले पिकअप गर्छ होला?
त्यो पिकअप गर्छ, त्यसमा मलाई एकदम डिटेल नलेज त छैन, तर त्यो चाहिँ युज गरिरहेका छन् अहिले मान्छेहरूले, त्यति चाहिँ थाहा छ मलाई. त्यो लेफ्ट ह्यान्डेड र राइट ह्यान्डेड हेलिसिटी भएको लाइटहरू युज गरेर यस्तो स्पिन टेक्सचरहरू प्रोब चाहिँ गरिरहेका छन्. जस्तो हजुरको चाहिँ इभन यो हल इफेक्टमा जब टाइम रिभर्स सिमेट्री ब्रेकिङ हुन्छ नि, इभन इन फेरोम्याग्नेट्स, हजुरको राइट ह्यान्डेड र लेफ्ट ह्यान्डेड हेलिसिटीको चाहिँ स्पेसली इन हामीले यसमा एक्सपेरिमेन्ट गरेका छौँ, त्यो रिजल्ट छ, त्यो पेपर लेख्ने बाँकी छ त्यसमा. त्यो कर इफेक्ट, इभन कर इफेक्टले पनि यो कुराहरू डिटेक्ट गर्छ, इभन फेरोम्याग्नेट पनि डिटेक्ट गर्छ. जस्तो हल इफेक्टमा जे देखियो त्यो कुरा चाहिँ इभन कर इफेक्टले पनि चाहिँ समात्छ. अप्टिकल स्टडिज गर्न मिल्छ यसमा.
हजुर त्यो त समात्छ. मेरो कन्सर्न चाहिँ कहाँनिर भयो भन्दा तपाईँको यो मेटेरियलमा चाहिँ एभ्री लेयर हेज अ डिफरेन्ट म्याग्नेटिक फिल्ड. त्यो भएको कारणले गर्दाखेरि बिकज अफ
दोस्रो मेटेरियलमा कुरा गर्नुभएको त्यो चाहिँ एभरेज स्ट्रक्चरलाई हेर्छ होला तिनीहरूले. एभ्री लेयरकोमा गएर भन्दाखेरि पनि हजुरले लाइटले स्टडी गर्दाखेरि चाहिँ त्यसको एभरेज अब हजुरले कतिको अब त्यसलाई मोनो लेयरमै जानुभयो भने चाहिँ अर्कै कुरा हो होइन. नत्र भए हजुरले बल्क स्याम्पलहरूमा स्टडी गर्नुभयो भने चाहिँ त्यसले त्यो एभरेज स्ट्रक्चरलाई चाहिँ हेर्छ होला रादर देन
एभरेजले. त्यो मुख्य प्रश्न नै त्यही हो. जस्तो तपाईँको चाहिँ तपाईँले 10-11वटा लेयरहरू प्लट गरेर देखाउनु भयो नि, त्यो एउटा लेयरबाट तपाईँको लेयर नम्बर 1 बाट 10-11 सम्म पुग्दाखेरि तपाईँको त्यो स्पिन रोटेसन हुँदै गयो होइन हेलिकली.
हजुर
मेरो कन्सर्न चाहिँ के भन्दा तपाईँको 10वटा लेयरलाई सबै एभरेज गर्ने हो भने जस्तो तपाईँले भनेको जस्तो कर इफेक्ट हेर्दाखेरि त त्यो अनफर्चुनेटली सबै क्यान्सल आउट हुन्छ कि भन्ने डर के.
त्यो हजुरको एकदम राइट कन्सर्न हो होइन. हाम्रो चाहिँ इभन त्यो हल इफेक्ट मेजर गर्दाखेरि पनि त्यो पहिला त त्यो हजुरको त्यो फ्लक्चुएसनले गरेन भने चाहिँ त्यो क्यान्सल हुन्छ. अनि फ्लक्चुएसनले के गरिदिन्छ भने त्यो राइट ह्यान्डेड र लेफ्ट ह्यान्डेड जुन हेलिक्स छ नि त्यसको पपुलेसनलाई चाहिँ चेन्ज गरिदिन्छ, सिफ्ट गरिदिन्छ. अनि त्यो सिफ्टले गर्दाखेरि चाहिँ अनि त्यो फिल्ड चाहिँ कपल गर्छ त्यो टेक्सचरसँग, अनि त्यसले चाहिँ त्यो हल इफेक्ट दिन्छ. त्यो इट्स अ भेरी गुड क्वेसन एक्चुअली. सो त्यही भएर नर्मल हेलिक्सहरूमा यो कुराहरू देखिँदैन. यो पर्टिकुलर यसमा पनि धेरै डिफ्रेन्ट हेलिकल फेजेस छन् नि, त्यो सबै हेलिकल फेजेस हुन्, अरूमा देखिँदैन. त्यो एउटा खाले ट्रान्सफर्स हेलिक्समा मात्रै देखिन्छ जसमा चाहिँ फिल्ड चाहिँ कपल गर्न सक्छ त्यो टेक्सचरसँग.
ओके, थ्याङ्क यू.
थ्याङ्क यू. अब नेक्स्ट म सबैलाई कसैलाई क्वेसन छ भने ह्यान्ड रेज गर्न रिक्वेस्ट गर्छु है, अब च्याट बक्समा भन्दा पनि. र माधव प्रसाद घिमिरे सर, प्लिज गो अहेड. माधवजी.
हजुर, थ्याङ्क यू राजु सर, थ्याङ्क यू भेरी मच. अनि निर्मल सरलाई I really appreciate and thank you for the very nice talk. है अनि मसित अब 2-4वटा क्वेशन्स त छ, अब कतिको टाइम हुन्छ Anyway, so सर त्यो स्लाइड नम्बर 19 मा यसो त्यहाँ सरले चाहिँ के मेन्सन गर्नुहुन्छ भन्दाखेरि एन्टी फेरोम्याग्नेटिक भनेर चाहिँ मेन्सन गर्नुहुन्छ यसो त्यहाँ जान मिल्छ सर
स्लाइड 19 मा
स्लाइड नम्बर 19
हजुर
कारण रेस हुन लाग्यो रेस
यस सर हो यसमा छ
हजुर
यसमा मैले यतापट्टि उसमा राइट साइडमा हेर्दाखेरि यसो हेर्ने हो भने चाहिँ एन्टी फेरोम्याग्नेटिजम देखाइरहेको छ हैन स्पिनको मैले गर्नु
हजुर
अनि सरले चाहिँ नन एन्टी फेरोम्याग्नेटिक
हैन यसमा कोलिनियर नै छ यसमा चाहिँ के छ भने हजुरको कोलिनियरले चाहिँ रेगुलर मेटेरियलमा चाहिँ बेरिफेज दिँदैन यसमा बेरिफेज आउनलाई चाहिँ यसको स्ट्रक्चरले हेल्प गरेको छ क्या यसमा चाहिँ यसको द वे यो चाहिँ अघि मैले हजुरलाई सुरुमा यसको मेटेरियलको इन्ट्रोड्युस गर्दाखेरि ब्रिफली चाहिँ एउटा कुरा के भनेको थिएँ भने देयर इज अ काइरल स्पेस ग्रुप भनेर भनेको छ अनि त्यो काइरल स्पेस ग्रुपमा चाहिँ के हुन्छ भने यसको सर्टेन मिरर प्लेनहरू सबै मिरर प्लेनहरू चाहिँ एब्सेन्ट हुन्छ यो काइरल स्पेस ग्रुपमा अनि त्यो मिरर प्लेनले गरेर चाहिँ त्यो रिफ्लेक्सनहरू नहुने भए हुनाले हजुरको चाहिँ यसमा चाहिँ कोलिनियर स्टेटले पनि त्यो हल कन्डक्टिभिटी चाहिँ नन जिरो बनाउन चाहिँ हेल्प गर्छ यदि त्यो स्ट्रक्चर त्यस्तो नहुनु हो भने चाहिँ हजुरको माइनस सिग्मा एक्स र त्यो सिग्मा एक्स वाई र माइनस सिग्मा एक्स वाई चाहिँ क्यान्सल भएर जान्छ त्यो क्यान्सल नहुनलाई चाहिँ यसको स्ट्रक्चरले हेल्प गरेको छ र अझ यसलाई हजुरलाई चाहिँ टेक्निकली भन्दाखेरि यसको जुन टाइम रिभर्सल सिमेट्री ब्रेकिङ चाहिँ कोलिनियर एन्टिफेरोम्याग्नेटमा हुँदैन हैन जेनरली अनि हल इफेक्ट आउनलाई चाहिँ टाइम रिभर्सल सिमेट्री इज अ मस्ट त्यो टाइम रिभर्सल सिमेट्री चाहिँ यसले कसरी पाउँछ भने यो डिफ्रेन्ट फ्रेम अफ रिफरेन्स जस्तो भयो क्या यसमा चाहिँ यो जुन क्रिस्टल स्ट्रक्चरले चाहिँ इभन कोलिनियर फेरोम्याग्नेटलाई एन्टिफेरोम्याग्नेटलाई पनि नन कोलिनियर जस्तो बनाइदिन्छ क्या त्यही भएर इट इज अ कम्बिनेसन अफ दिस क्रिस्टल स्ट्रक्चर त्यही भएर तिनीहरूले यतापट्टि लेफ्ट ह्यान्डेड राइट ह्यान्डेड स्ट्रक्चर देखाएको छ नि मिरर प्लेन राखेको छ नि त्यो चाहिँ त्यो दुईटाको कम्बिनेसनले चाहिँ यसमा चाहिँ टाइम रिभर्सल सिमेट्री ब्रेकिङ चाहिँ हुन्छ अनि त्यही भएर त्यसले चाहिँ सर्टेन बेरी कर्वेचर जेनेरेट गर्छ अनि फाइनाइट कन्डक्टिभिटी आउँछ इट इज भेरी इन्ट्रेस्टिङ दिस पिपल आर इन कन्ट्याक्ट विथ मी नाउ and hopefully we can have some collaboration with these guys through Igor. So Igor knows very well these people and then you know we might do some sort of collaboration with these people. And interesting thing के छ भने उनीहरुको भ्यालु चाहिँ हाम्रो मैले मेजर गरेको भ्यालु सँग कन्डक्टिभिटी यहाँ मैले देखाइन 27 थियो त्यसको त्यो साइमन्स पर सेन्टिमिटर उनीहरुले चाहिँ एक्ज्याक्टली त्यति नै भ्यालु निकालेको छन् के क्याल्कुलेसन गरेर पनि
त्यही त फेरि यहाँ मैले के देख्दैछु भन्दाखेरि हल कन्डक्टिभिटी हेर्दाखेरि अब दुईटा अपोजिट डाइरेक्सनमा तपाईले कम्पेयर गर्नुभयो भने चाहिँ दे आर कम्प्लिटली ओभरल्यापिङ विथ इच अदर एन्ड द्याट इन्डिकेट्स द्याट इट इज क्यान्सलिङ मिन्स ओभरअल शुड बी 0 हैन अनि अब त्यो हो भने त क्रिस्टलले चाहिँ कसरी ठ्याक्कै
छैन यो इनहरुले उ गरेको छ नि त यहाँ नेट यहाँ प्लट गरेको छ नि
आई सी त्यो नेट
त्यो ब्लू लाइन प्लट गरेको छ नि यसमा क्यान्सल हुँदैन यसको मेन यो चाहिँ भर्खर साइन्स एडभान्समा पब्लिस भएको छ यो उनीहरूले ऊ चाहिँ लगभग 1 वर्ष अगाडि नै आर्काइभमा राखेका थिए तर यसमा क्यान्सल हुँदैन त्यो नहुनुमा चाहिँ अनि यिनीहरूको मात्रै होइन अहिले चाहिँ क्रिस्टियन बटिस्टाले यो अर्को यो पेपरमा चाहिँ he's a very you know well known scientist and उनीहरूले गरेको यो क्याल्कुलेसनमा पनि त्यो चाहिँ काइरल क्रिस्टलहरुमा चाहिँ कोलिनियर एन्टिफेरोम्याग्नेटले पनि एनोमलस हल इफेक्ट जेनेरेट गर्न सक्छ भनेर यो चाहिँ अहिले एकदम नयाँ ट्रेन्ड हो र मान्छेहरूले यसलाई फलो गरिरहेका छन् धेरै
हजुर हजुर ओके सर सर त्यो स्लाइड नम्बर 22 मा यसो जान
मिल्छ सर
Sorry, Raju sir, I have just 2 questions now.
Sure. Ask.
हजुर अनि यहाँ चाहिँ जुन सरले कम्प्लेक्सिटी इन म्याग्नेटिजम भन्ने त्यहाँ जुन देखाउनु भएको छ
हजुर
यो J1 and J2 are basically the couplings, right?
त्यो चाहिँ एक्सटेन्ट कन्स्टेन्ट हजुर एक्सटेन्ट कन्स्टेन्ट चाहिँ हजुरको अब यसमा के भयो भने यो म्याग्नेटिज एटमहरु चाहिँ सबै क्रिस्टलोग्राफिकली इक्विभ्यालेन्ट साइटमा छ दे आर अल इक्विभ्यालेन्ट तर के छ भने यो दुईटालाई सेपरेट गर्ने चाहिँ छ नि यो ब्लक चाहिँ डिफ्रेन्ट छ क्या त्यही भएर यिनीहरूले चाहिँ अब इन प्लेनमा त भेरी स्ट्रङ फेरोम्याग्नेटिक कपलिङ छ सो त्यहाँ Kagome फ्रस्ट्रेसन यसमा इन प्लेन चाहिँ छैन इट्स भेरी यु नो मेबी 2 orders अफ म्याग्निट्युड लार्जर छ इन प्लेन कपलिङ चाहिँ अनि तपाईँको सी एक्सिसतिर जानुभयो भने चाहिँ यो र यो यसको कपलिङ चाहिँ र यसको कपलिङ चाहिँ डिफ्रेन्ट छ त्यो भएपछि यसले फ्रस्ट्रेसन इन्ड्युस गर्यो नि प्यारामेट्रिक फ्रस्ट्रेसन इट्स नट अ जियोमेट्रिकल फ्रस्ट्रेसन अनि त्यसले गर्दाखेरि चाहिँ हजुरको डिफ्रेन्ट यु नो कम्प्लेक्सिटी चाहिँ जेनेरेट गर्छ अनि त्यो चाहिँ क्याल्कुलेसनमा इगोरले चाहिँ एभ्री डिटेल्स चाहिँ पिक गरेको छ
हजुर त्यो एउटा रिजन मैले यहाँ देख्दाखेरि चाहिँ एउटा अर्को रिजन के पनि हो भन्दाखेरि त्यो जुन लेयर छ म्याग्नेटिक लेयर छ भनौँ न ब्लू एटम्स एउटामा ब्लू एटम्स इन्क्लुड भएको छ अर्कोमा चाहिँ मिक्सचर अफ टिन र अर्को एटम्स भएको
हो यो ब्लू र रेड दुईटै टिन हो यो इनइक्विभ्यालेन्ट साइडका टिनहरू हुन् यसमा चाहिँ टिन मात्रै छ हजुर टिन मात्रै छ यसमा चाहिँ इट्रियम र टिन छ अनि इट्रियम भएपछि त यो अर्कै एन्टिटी भयो नि अनि त्यही भएर अनि थिकनेस पनि फरक छ यो दुईटा लेयरको अनि त्यसले पनि यो जे चाहिँ स्लाइटली डिफरेन्ट छ
हजुर अनि सर just next slide में जाऊँ ना सर I have lots of questions but only one last so here you have shown very interestingly about this complex magnetic feature of this material अनि यहाँ चाहिँ जुन spin rotation मैले देखिरहेको छु हैन अघि बङ्गु सरले पनि त्यसैमा बढी कन्सर्न गर्नु भएको थियो सो यहाँ जुन तपाईले भनौँ एक्सपेरिमेन्टली त इट इज फाइन आई विल से हैन म्याग्नेटिजमको केस हामीले मेजर गर्ने हो पर आई थिंक वी कैन ऑब्जर्व दैट नाइसली बट इन टर्म्स अफ डीएफटी व्हेन आइगर इज डूइंग हाउ वाज ही डीलिंग विथ दिस रोटेशन आई मीन one position मा छ इन प्लेन राइट
हजुर
पोजिसन फिफ्थ लेयर मा छ आउट अफ प्लेस सरी
त्यो एंगल डिफाइन गरेको छ उले यो अल्फा र बीटालाई डिफाइन गरेको छ अनि अल्फा चाहिँ माइनस सुरुमा उसले क्याल्कुलेट उसको अनि त्यसलाई चाहिँ उसले त्यो फर्स्ट प्रिन्सिपल क्याल्कुलेसनबाट ह्यामिल्टोनियन यो ह्यामिल्टोनियन छ नि म त्यसमा एक्सपर्ट चाहिँ होइन तर मैले अस्तिको हप्ता मात्रै पेपर सबमिट गरे भएर यसको इन्फर्मेसन चाहिँ ताजै छ मलाई थ्योरीको सो यो जुन फुल ह्यामिल्टोनियन लिएको छ यो फुल ह्यामिल्टोनियनलाई फर्स्ट उसले के गर्यो भने यो यसमा चाहिँ डिफ्रेन्ट लिएको छ यसमा चाहिँ इन्टरप्लानर एक्सचेन्ज जुन यता छ जेपी चाहिँ भेरी स्ट्रङ छ यसमा अनि त्यसपछि इन्ट्राप्लानर एक्सचेन्जहरू जुन छ नि यो इन्ट्राप्लानर एक्सचेन्ज चाहिँ यहाँ J1 देखि J6 सम्म लिएको छ यो डिफाइन गरेको छ डिफ्रेन्ट लेयरमा अनि आइजिङ एनाइसोट्रोपी लिएको छ अनि त्यसपछि आइजिङ एक्सचेन्ज लिएको छ सरी सिंगल साइड एनाइसोट्रोपी लिएको छ आइजिङ एनाइसोट्रोपी लिएको छ त्यसपछि जिमेन इफेक्ट सबै राखेर अनि त्यसलाई चाहिँ डीएफटीले क्याल्कुलेट गरेर अनि त्यो एनर्जी मिनिमम स्टेट आउने बेलामा उसले एंगल चाहिँ पाएको एंगल चाहिँ एक्सपेरिमेन्टल्ली अब्जर्भ एंगलसँग लगभग मिल्छ अनि त्यसरी डीएफटीले क्याप्चर गरेको अनि त्यसलाई चाहिँ फेरि मिन फिल्ड ले चाहिँ मोडलिङ गरेर त्यो इनफिल्ड क्याल्कुलेसनहरू चाहिँ मिन फिल्ड क्याल्कुलेसन हो
okay so that is nice अनि भनेपछि एकपालि फेरि त्यसमा जस्ट ब्याक गरौँ न सर
हस्
अनि त्यहाँ जुन म्याग्नेटिजमको कुरा त्यहाँ आएको छ नि सर त्यो इन प्लेन र आउट अफ प्लेन भनेपछि यसमा उले मेजर गर्दाखेरि सिम्पली हार्ड एक्सिस र इजी एक्सिसलाई उले कन्सिडर गरे अनि त्यहाँबाट एंगल अल्फाको रेस्पेक्टमा रोटेट गरेर के म्याग्नेटिजम के कस्तो खालको ओभरअलमा आउँछ त्यो मेजर त्यो आइडेन्टिफाई गर्यो पहिला
हजुर एकदम हो
ओके थ्यांक यू सर थ्यांक यू
यू आर वेलकम
Thank you. That's very nice.
Yeah, this is very complex theory. I think it would not have been possible without Igor being here and seeing this data. So
yes, exactly. Sir, one more last question. Sorry, I'm sorry. Yeah. So यहाँ चाहिँ तपाईले जुन देखाउनु भएको छ एरोले पनि इन्डिकेट के गरिराखेको छ भन्दाखेरि तपाईको म्याग्नेटिजम हरेक लेयरमा इन्क्रिजिङ र डिक्रिजिङ अर्डरमा गइराखेको छ हैन यो इन्क्रिजिङ र डिक्रिजिङ अर्डरमा तपाईले एक्सपेरिमेन्टली पनि यही भनिम न हरेक लेयर डिपेन्डिङ अन लेयर साइज डज इट इन्क्रिज अर डिक्रिज
हामी हैन त्यो यो इन्क्रिज र डिक्रिज भएको चाहिँ तपाईको प्रोजेक्सनले हो किनभने आई क्यान नट ह्याभ अ 3 डाइमेन्सनल थिङ प्रोजेक्टेड इन अ 2 डाइमेन्सनल थिङ है त्यो यसको मोमेन्ट साइज चाहिँ यसले गरेको छैन खाली डाइरेक्सन मात्रै देखाएको हो त्यही भएर मोमेन्ट साइज चाहिँ डोन्ट गो आफ्टर द मोमेन्ट साइज इट्स जस्ट द डाइरेक्सन because I don't have any tool to I drew this figure myself, so I don't have any tool to draw a 3-dimensional object in a 2-dimensional plane. So it's just related to that.
Okay, thank you.
Okay, Madhav sir, I know you have more questions, but others are also waiting to ask. अनि त्यसपछि तपाईको क्वेशनको पनि अरु फर्दर एन्सर आउँछ.
I'm
This
sorry.
is the beginning. You can collaborate
No,
further.
these are all
Thank you so
interesting
much.
and
Ra
valid
next,
questions.
I request Gyanendra iPhone भनेपछि Gyanendra ji, please.
Thank you, sir. Nirmal Bhai, namaste.
Namaste, Gyanendra bhai.
मेरो क्वेशन चाहिँ त्यति जान्छ. Is it an artificial sample? किन भन्दाखेरि
I think it is. मैले दाइलाई पठाइदिन्छु भनेर कुरा गरेको छु. अब हेरौँ के हुन्छ ल्याब खोलेपछि. यसमा चाहिँ यस्तो थियो, मैले चाहिँ यो आरपिएस हामीले गर्न लागेका थियौँ, यो कोभिडले गरेर रोक्यो. यसमा चाहिँ इन्ट्रेस्टिङ टोपोलोजिकल प्रपर्टी पनि भेटेका छौँ हामीले यसमा धेरै एक्सपेरिमेन्ट गरिसकेका छौँ है. एक्सेप्ट आरपिएस यसमा अरू 2-3 पेपरहरू आउँछन् अब लगभग यो गएपछि. अनि इभन क्वान्टम ओसिलेसनहरू सबै देखेको छ यसमा. अनि आरपिएस त्यो क्लिप गर्न चाहिँ अलिकति गाह्रो छ भनेर भन्थ्यो. अब उसको त्यो रोकिया भएर तपाईहरुको ल्याबमै गर्न मिल्छ भने चाहिँ त्यहाँ पठाउने.
अहिले हाम्रोमा चाहिँ प्रिपरेसन च्याम्बर नयाँ राखेका छौँ. त्यो भएपछि क्लिपिङमा चाहिँ धेरै प्रब्लम नहोला.
म अस्ति कुरा गरेको थिएँ दाइसँग.
त्यही इन्ट्रेस्ट लाग्यो. त्यो अलिकति बढी मेटालिक भएको भएर चाहिँ
होइन यो चाहिँ अलिकति जस्तो स्ट्रक्चरमा लेयर देखिएको छ नि त्यो कोबाल्ट 93 सल्फर 6 जस्तो चाहिँ छैन. अनि त्यो पहिला मैले तपाईलाई पठाएको स्याम्पल जस्तो गाह्रो पनि छैन. यो चाहिँ इन्टरमिडिएट होला.
त्यो क्लिप त भएको थियो. त्यो चाहिँ तपाईको त्यो अर्को थियो नि त्यो थ्रीफोल्ड डिजेनेरेट नोडल लाइन थियो नि. त्यो चाहिँ धेरै ट्राई गरे, क्लिपै भएन.
त्यो चाहिँ अहिले गरेको छ के त्यो आर्गनको मान्छेले.
सायद तिनीहरूले त्यो स्पटरिङ गरेर गर्यो होला हैन.
खै कसरी गर्यो गरेको छ
एकदम गाह्रो भएको थियो त्यो. Thank you.
Okay, thank you, Gananji. Next, Sanju Shrestha. Sanju madam, please.
Sir, मेरो क्वेशन चाहिँ नि म्याग्नेटिक मेटेरियलहरु तपाईहरुले ग्रो गर्नुहुँदा सबस्ट्रेट चाहिँ के युज गर्नुहुन्छ?
यसमा सबस्ट्रेट हैन म्याम, यो चाहिँ सिंगल क्रिस्टल नै हो.
सिंगल क्रिस्टलै.
हजुर. त्यो जुन नेचरमा पाइन्छ नि क्रिस्टलहरु अनि त्यस्तै क्रिस्टलहरु बनाउँछौँ. अनि त्यो चाहिँ डिफ्रेन्ट टेक्निक हुन्छ. कहिलेकाहीँ चाहिँ त्यो जस्तो हजुरलाई भन्दाखेरि चाहिँ यहाँ चाहिँ अब मैले अलिकति यहाँ राखेको एउटा स्लाइडमा पनि छ, त्यो मैले भनिनँ. यहाँ यसमा चाहिँ यो केमिकल भेपर ट्रान्सपोर्ट हो. यो चाहिँ क्रिस्टल ग्रो गर्दाखेरि चाहिँ पहिला हामी पाउडर बनाउँछौँ त्यसको. त्यो ट्युबमा इनर्ट एटमोस्फियरमा राखेर अनि हिट गरेर डिफ्रेन्ट केमिकल राख्यो. अनि केमिकलहरुलाई हिटले रियाक्ट गर्यो. वन्स रियाक्ट भइसकेपछि चाहिँ हजुरको यस्तै यो छ नि यो क्वार्ट्ज ट्युब, सिल्ड क्वार्ट्ज ट्युबमा आयोडाइन राख्ने. अनि आयोडाइन राखेर त्यसको टेम्परेचर मेन्टेन गर्यो भने चाहिँ कस्तो हुन्छ भने आयोडाइन चाहिँ 150 केल्भिनमै त्यो बोइल भइहाल्छ. 150 सेन्टिग्रेडमा बोइल भइहाल्छ. अनि बोइल भएपछि चाहिँ भेरी रियाक्टिभ हो नि त आयोडाइन त. अनि आयोडाइनले यहाँ सबै मेटेरियलमा हुँदैन, तर मोस्ट अफ द मेटेरियललाई चाहिँ रियाक्ट गर्छ. अनि रियाक्ट गरेर यहाँ चाहिँ हट जोन हुन्छ, यहाँ चाहिँ कोल्ड जोन हुन्छ. युजली त्यो रिभर्स पनि हुनसक्छ डिपेन्डिङ अन एक्जोथर्मिक र इन्डोथर्मिक रियाक्सन. अनि त्यसले के गर्छ भने त्यो आयोडाइनले यो यहाँको मेटेरियललाई पिकअप गर्छ इन भेपर फर्म. र अनि यहाँ प्रेसर बिल्डअप हुन्छ. यहाँ हट भएपछि यतापट्टि चिसोतिर जान खोज्छ. चिसोतिर गएपछि चाहिँ त्यो हेभी हुन्छ त्यहाँ गएपछि. अनि हेभी भएपछि त्यसलाई त्यो आयोडाइनले छोडिदिन्छ त्यसलाई त्यहाँ. अनि त्यसपछि त्यो फेरि के हुन्छ भने यहाँ प्रेसर बिल्डअप हुन थालेपछि त्यो आयोडाइन पुस्ट ब्याक हुन्छ. अगेन यहाँ गएर रियाक्ट गर्छ. अनि आएर यहाँ जसरी यो पिक्चरमा देखाएको छ नि त्यसै गरेर यहाँ चाहिँ क्रिस्टलहरु चाहिँ फर्म हुन्छ. यो क्रिस्टल चाहिँ कहिलेकाहीँ चाहिँ एकदम ठुलै पनि हुन्छ क्या. जस्तो यसमा यो पिक्चरमा मैले देखाएको 1/1 मिलिमिटरको भनेको यो चाहिँ हजुरको लगभग हाफ सेन्टिमिटर 5 मिलिमिटर लामो क्रिस्टल छ. त्यो भनेको चाहिँ हाम्रो न्युट्रोनको लागि चाहिँ सानो हुन्छ, तर हामीले गर्ने मेजरमेन्टमा त मोर देन इनफ. मलाई 1 मिलिमिटरको क्रिस्टल भयो भने मेजर गर्नलाई इनफ हुन्छ. अनि अर्को कस्तो पनि हुन्छ भने हजुरको त्यो अर्को फ्लक्स मेथड भन्ने हुन्छ. हामीले चाहिँ त्यसलाई कुनै अर्को मेटलमा राखेर डिजल्भ गर्छौँ. अनि त्यसपछि त्यो प्रेसिपिटेट गरेर अनि सेन्ट्रिफ्युज गरेर त्यो फ्लक्स फालेर अनि क्रिस्टलहरु पनि निकाल्छौँ.
हजुर, अर्को एउटा चाहिँ नि जस्तै तपाईले देखाउनु भएको डाटा चाहिँ सबै 001 प्लेनमा छ नि.
हजुर हजुर
अनि यसमा चाहिँ हजुर प्लेनको ओरिएन्टेसनको सँग पनि त त्यसको भ्यालुहरू त फरक हुने होला हैन
एकदम फरक हुन्छ
के छ
त्यो चाहिँ ओरिएन्टेसन गर्नलाई क्यारेक्टराइजेसन हामी एक्सरेबाट चाहिँ त्यसको ओरिएन्टेसन निकाल्छौँ अनि धेरै जसो ओरिएन्टेसन चाहिँ इभन त्यो पाउडर डिफ्र्याक्टोमिटरले पनि हजुरको स्याम्पल थिन बनाएर राख्यो भने त्यसले 001 हो कि अथवा 100 पिकहरू हो त्यो दिइहाल्छ हेक्सागोनल चाहिँ अलिकति कम्प्लिकेटेड हुन्छ एबी प्लेन निकाल्न चाहिँ सी एक्सिस चाहिँ त एकदम इजिली थाहा पाइन सकिन्छ स्पेसली यो फ्लक्स ग्रोन क्रिस्टल र यो भेपर ट्रान्सपोर्टेड क्रिस्टलहरूको चाहिँ सेप पनि हजुरको यसमा हेर्नुभयो भने सेपमै आएको हुन्छ क्या हेक्सागोनल क्रिस्टल हेक्सागोनल सेपमा आइरहेको हुन्छ त्यो भएपछि हजुरको सी एक्सिस थाहा भइहाल्छ अनि ए र बी पत्ता लगाउनलाई कुरो मात्रै हो त्यो एक्सरेले तुरुन्तै पत्ता लाग्छ त्यसमा गाह्रो अनि अलिक कम्प्लिकेटेड छ भने चाहिँ त्यो लावे डिफ्र्याक्सन गर्नुपर्छ अथवा सिंगल क्रिस्टल डिफ्र्याक्सनले पनि पत्ता लाग्छ
अनि त्यो रिजल्टहरु चाहिँ सबै एउटै प्लेनमा देखाउनु भएको चाहिँ के
त्यसमा मात्रै इन्ट्रेस्टिङ भयो हैन त्यसमा मात्रै अर्को जस्तो हजुरलाई चाहिँ यसमा मैले यसमा चाहिँ त्यस्तो देखाएको चाहिँ यो प्रपर्टी चाहिँ सी एक्सिस पट्टिको यो एच परपेन्डिकुलर यो चाहिँ प्लेनमा भयो परपेन्डिकुलर टु 001 भनेर सी एक्सिस भयो अनि सी एक्सिसको परपेन्डिकुलरमा भयो यो चाहिँ सी एक्सिसमा प्यारललमा भयो सी एक्सिसको प्यारललमा चाहिँ यो बोरिङ छ केही पनि छैन लिनियर ग्रोथ छ हैन अनि अल द इन्ट्रेस्टिङ प्रपर्टिज ह्यापन इन द प्लेन त्यही भएर अरु अब सबै मेजरमेन्ट चाहिँ फोकस त्यसैमा भयो
हस् थ्यांक यू
युर वेलकम अनि जस्तो यही क्रिस्टलमा पनि हजुरको यो चाहिँ हेर्ने बित्तिकै थाहा हुन्छ कि हामीलाई यो हेक्सागोनलै सेपमा छ नि यो चाहिँ फ्लक्स ग्रोन क्रिस्टल हो अनि यो चाहिँ सी एक्सिस हो अनि यहाँ चाहिँ लगभग यो लाइन चाहिँ म युज टु भइसकेको छु यो लाइन चाहिँ हजुरको ए एक्सिस हुन्छ यसमा अनि त्यो तुरुन्तै भेरिफाई पनि गर्न मिल्छ त्यो लगभग यो हो भएपछि पलिस गरेर अनि एक्सरेमा राख्यो भने थाहा भइहाल्छ अब न्युट्रन गर्दाखेरि त न्युट्रनले जुन डिरेक्सनमा पनि हेर्न सक्छन् तिनीहरूले
हस् थ्यांक यू
थ्यांक यू सन्जु म्याडम र अब विशेष निर्मल जीलाई विशेष धन्यवाद एक्सिलेन्ट प्रेजेन्टेसन र इन्टरेक्सन पनि एकदमै राम्रो भयो आई एम सो ह्यापी र विनिल सर
थ्यांक यू सो मच फर प्रोभाइडिङ मी दिस अपर्च्युनिटी
थ्यांक यू एभ्रीवन सबैजनालाई धेरै धेरै धन्यवाद खास गरी स्पिकरलाई यो एकदमै इम्पोर्टेन्ट टक र नयाँ एरिया एक्सप्लोर गर्ने लिड गर्ने हो हामीलाई अलिकति थाहा छ Thank you very much and thanks to the TU faculties for धेरैजना आउनुभएको छ मेटीदेखि माकालीसम्मका हाम्रा TU का फिजिक्सका सरहरू धेरै धेरै धन्यवाद त्यस्तै विदेशबाट आउनुभएको विदेशबाट एटेन्ड गर्नुभएको थुप्रैजना सरहरू हुनुहुन्छ थ्यांक यू यति भन्दै मैले अहिले क्लोज गर्न भन्दा अगाडि हाम्रो स्टुडेन्टहरु अहिले पनि सुनिरहेछन् साइलेन्टली सुनिरहेछन् है मैले यसो चेक गर्दाखेरि फर्स्ट सेमेस्टर थर्ड फोर्थ सेमेस्टर इभन सेकेन्ड सेमेस्टरका स्टुडेन्टहरु पनि छन् केही कुराहरु लास्टमा राखिदिन स्टुडेन्टहरुको लागि मात्रै म स्पिकर डाक्टर निर्मल घिमिरेलाई म रिक्वेस्ट गरे स्टुडेन्टलाई मात्रै केही सेन्टेन्स केही कुराहरु भनिदिनु त्यसपछि म क्लोज गर्छु र क्लोज म अफिसियली गर्छु इन्फर्मल 5-10 मिनेट हामी केही कुराकानीहरु बाँकी छ भने हामी बीचमा पनि ती कुराकानीको लागि केही समय हामी कुर्छौं 10 मिनेट राजु सर म अब निर्मल स्पिकरलाई मैले अनुरोध गरे स्टुडेन्टलाई केही कुरा भनिदिनु त्यसपछि हाम्रो यो सेसन
स्टुडेन्टलाई इन्ट्रेस्टिङ सर थ्यांक यू स्टुडेन्टलाई चाहिँ म के भन्न चाहन्छु भने यु आर इन राइट प्लेस त्यहाँ नेपालमा चाहिँ अहिले जुन मास्टर्स गर्ने चाहिँ त्यहाँको मास्टर्स लेभल पढाइ चाहिँ निकै राम्रो हुन्छ र त्यो पढ्दाखेरि चाहिँ स्पेशली किनभने when you are doing masters in physics the idea is to go and do PhD and go into the research field त्यो रिसर्च फिल्डमा चाहिँ अन्डरस्ट्यान्डिङ त्यो बेसिक कुराहरू चाहिँ बुझ्नु चाहिँ एकदमै धेरै इम्पोर्टेन्ट हुन्छ त्यो पढाइ चाहिँ त्यसरी अहिलेबाट त्यसरी लगिजानु भयो भने चाहिँ त्यसले चाहिँ पछि एकदमै ठुलो हेल्प गर्छ त्यो सानो कुराहरू जस्तो हामी चाहिँ म यहाँ एउटा कुरा सेयर गरौँ है सरले मलाई अपर्च्युनिटी दिनुभएको बेलामा म मास्टर्स पढ्दै गर्दाखेरि मेरो एकजना रिलेटिभ हुनुहुन्थ्यो, उहाँ चाहिँ ल पढिराख्नु भएको थियो। अनि उहाँले चाहिँ मलाई यो फिजिक्स किन पढायो भनेर सोध्नुभयो। अनि उहाँलाई चाहिँ के लाग्दो रहेछ भने फिजिक्स भनेर चाहिँ यो गुम्बामा यो अफेन्सिभ नहोस्, गुम्बामा चाहिँ बौद्ध शिक्षा पढेको जस्तो हो, किनभने त्यसको युज भनेको चाहिँ उहाँले भनेको टर्म युज गरेको हो, मैले ल अन्यथा नलिनु होला। अनि त्यसमा चाहिँ के भने यसको काम भने फेरि नेक्स्ट जेनेरेसन मान्छेलाई पढाउने, हाम्रो नेपालको स्थितिमा उहाँले दिए उदाहरण। अनि त्यसपछि फेरि त्यसबाट नेक्स्टमा पास हुने, फेरि टिचर हुने, अनि त्यसलाई नेक्स्ट जेनेरेसनमा पास गर्ने, अनि त्यो मात्रै हो, त्योभन्दा बढी चाहिँ के हुन्छ भनेर उहाँले मलाई भन्नुभएको थियो। अनि तर म त्यसको चाहिँ अगेन्स्टमा थिएँ होइन। अनि अहिले हामी चाहिँ त्यही काम गरिरहेका छौँ क्या। इट्स नट जस्ट पासिङ अफ नलेज, we actually can we have to believe that we can change this world through जुन कुरा मैले सुरुमा भने त्यो चाहिँ कुनै एक्जाजरेटेड कुरा हैन। अब मेरो लाइफ टाइममा मैले गर्न नसकमला, तर म जस्तै रिसर्च गर्ने अरु मान्छेहरुले चाहिँ पत्ता लागेको कुराहरुले चाहिँ यो वर्ल्ड चेन्ज हुन्छ, चेन्ज भएको छ। र यो चाहिँ you are in a right track. Just try to understand the fundamental things. I think that is more important than anything else at this point of career. त्यति हो सर मेरो भन्नु।
थ्यांक यू। अब मैले यो अफिसियली चाहिँ मैले क्लोज गरे। राजु सर अब केही कुरा इन्फर्मल हाम्रो शेयरिङहरु छ भने चाहिँ गरौँ, त्यसपछि म 5 मिनेट पछाडी म सेसनलाई एन्ड गर्छु। 5 मिनेट 7 मिनेट।
उसो भए दिनेश सर रेकर्डिङ अफ गर्दियौ है उसो भए। स्टप गरौँ।